Okay, today's lesson is about gravitational force and weight. So let's start with gravitational force. Gravitational force is the force between masses. It's always attraction force, and it is due to mass on another mass. Okay, so let's say we have two masses, M1 and M2. At some distance r. So the force of attraction between these two masses is going to be considerable, or it's going to be observable on one or the other, or on both, when both masses are big enough or one of the masses is big enough. If both masses are small or too small, the force is too small to observe. The effect of the force is going to be too small to observe. Okay? So the force of attraction, as the universal gravitational law of Newton says, states, it is directly proportional to the product of the masses and inversely proportional to the square of the separation. It is an inverse square law. So it is given as Fg, gravitational force, is a constant, universal gravitational constant, G, times mass 1 times mass 2 over the distance between the two masses squared. And G is in the order of 10 raised to minus 11. Some constant, I think 6.7 something times 10 raised to minus 11. In this order, whenever your masses are too small, the force is going to be very small to observe. But it exists. Always. And the force is always attraction. Okay? It's always attraction. And it is going to be, let me say, this is the gravitational force by mass 2 on mass 1. The same force in the opposite direction is exerted by mass 2 on mass 1 by mass 1 on mass 2. These two forces are equal and opposite. They are action and reaction forces. The point here is whether this is too big, and this too small, or vice versa, or they are equal or approximately similar in mass. The forces are going to be always equal. Okay? That's why, that's because they are action and reaction. Call one action, the other is automatically reaction. Okay, these are equal and opposite forces exerted by one another on each other, and they are always acting on two different bodies. But they do not cancel each other because they act on two different bodies. This is what the law says. To make this one clear, let's consider one of the masses is Earth. And maybe the other is going to be Moon, or maybe you can bring some object closer to it, and let's say a satellite or an object at some distance from the Earth with mass m. In this case, because the mass of Earth is big enough, you can see the effect of the gravitational force of attraction of the Earth on the smaller mass. And we write the gravitational force is going to be G, the universal gravitational constant, times mass of Earth times the mass of the object, which is in attraction in the field of Earth actually. But again, don't forget that this mass attracts Earth by equal magnitude of force. By equal magnitude of force. But the mass of the Earth is too big. That force may not affect Earth. It automatically affects the smaller mass. Okay? So you have the equation to be like this, and this one is what we call G, the gravitational acceleration towards the center of the Earth due to Earth's attraction, times mass. Okay, this is G, which is 9.8 meters per second square basically, on average, and it is small here and it is large here, and the average is taken to be this one. Okay, so this is what you call weight. Okay, this is what we call weight of n. Weight basically now is what? Gravitational force. It is net force on an object due to Earth's attraction. Okay? So it is a kind of mass times acceleration. It is a kind of mass times acceleration. It is net force because it is about meters second law. Net force on an object is mass times acceleration, and the acceleration is specific, which is G, 9.8 meters per second square on average on the surface of the Earth. Okay, so weight is a net force, and it depends on what the mass, because G is going to be the same on average on the surface of the Earth, and this weight basically, like G, you can say, if this is Earth, according to this expression, either G or mg has to increase as we go from some altitude outside the Earth, from the surface to Earth's center. Automatically, G or mg increases. Okay? Through this Earth. The question is, when you come here, okay, because you have G is equal to G mass of Earth over R squared measured from the center of the Earth. As we go, G and M are constants, and R is going to be decreasing. And due to the decrease in R, the force of gravity or gravitational acceleration is going to increase as we go from some altitude to the surface and crossing the surface to the center of the Earth. Okay? And the mathematics says at R is equal to 0, G has to approach into infinity. Okay, that's what the mathematics says. And here comes the confusion. That's why we say mathematics is not physics, physics is not mathematics. Physics cares about physical interpretation of equations, but mathematics is not. Okay? They will say this one is singularity, but in our case we deal with what? Physical interpretation. So when you come here as a center, what happens is, up to this, G increases, yes, but at this point, it is going to be according to the symmetry. You will have equal mass either side of the center, equal mass. So an object at this point is going to be equally attracted out to the right as to the left, up to the down, in each direction from the center. It is going to be equally attracted. Therefore, the net attraction is going to be what? 0. So instead of G approaching to infinity at the center, G is physically 0. G is physically 0. This is what people usually confuse with. So as the center of Earth, the gravitational attraction of Earth on objects and its acceleration G are 0. They are 0. And another point related to this one is if you consider, Earth, let's say it should be a little bit bulged as the equator, let's say that you have somebody somewhere here, and we have another one somewhere here, and if somebody asks you which one is more attractive, let's say at the same latitude, both are at the same latitude. The only difference is one is in the northern hemisphere, closer to the North Pole, the other is to the South Pole. People try, usually if you just pick globe, the model, you can put an object at that point, but you can't put at the bottom because of gravitational attraction of the Earth's force. But for Earth, which is in space, this and this two people are going to experience the same gravitational force. No falling here, It is up for the one who is standing here, the same up. Though they face different direction in space, they are going to say that's up and this up, And this is another point that people usually confuse with. So try to think and figure out based on what? Based on the gravitational force of the Earth, because that's due to Earth's gravitational field, which is always to the center. So be anywhere around the Earth, the attraction is to the center, and away from the center is going to be your up, which you try to move against the Earth's gravitational field. To the center, you fall without any difficulty, with no resistance. Thank you for today. For next time, I will come up with some more misunderstood concepts. See you with the next video. Bye.